All right, so now let's talk about VSEPR for organic chemistry. So what's different? Well, fundamentally, I actually don't care so much about valence shell electron pair repulsion theory. What I do care about, however, is the structure. The way the structure is actually put together, what the bond angles are, what the geometry of the structure is. And so what I've drawn for you right now are 4 bad things that I don't ever want to see drawn anymore. Because they're wrong, and they're wrong in very specific ways that have to do with getting the geometry wrong. And there's an underlying reality here that we're trying to describe. The reason why we draw structures out is because we're trying to represent what they actually look like, what their shape really is. And the underlying reality is the reason why they are the way they are is because of valence shell electron pair repulsion theory. What you're trying to do is push the atoms as far apart as possible, but you're constrained in some sense by the orbitals involved. So what's underlying all of the geometry things I'm going to talk about right now is actually atomic and molecular orbitals. So we'll talk about that in a little bit. But if you draw a molecule like this, methane, drawn out this way, it drives me nuts. Is it correct from a Lewis structure perspective? True, yes, absolutely. But that's not the way this molecule is going to look like. What's the best you can do to spread things out as far as you can in 2-dimensional space? 90-degree bond angles, as drawn. However, that is not the way the molecule actually looks. When you have 3-dimensional space available, the way methane is going to look instead is going to look rather more like this. So the carbon atom is at the center of a tetrahedron, and the bond angles involved here are 109.5 degrees. Okay, so what's wrong with this picture? Well, I like the 109.5 degrees implied by this bond angle right here, the carbon to the carbon that you see, and this hydrogen doesn't necessarily offend me. This hydrogen, however, these bond angles are much too acute. That just does not look right. So the correct way of representing this molecule, if you're going to draw out those hydrogens for the central atom, would be to put them up like this. One of the 2 hydrogens involved is going to be going toward you, and that will be represented by the wedge, and one of them is going to be going sort of away from you, and that's going to be represented by the hash. So in any event, what you're going to have in the molecule is bond angles that are 109.5. You've got this staggered conformation here. We're going to talk more about that much later. But the other 2 angles involved need to be implied to be 109.5, which is to say greater than 90 degrees. So that's what you're trying to do with that. What's the problem with water? Well, as drawn, of course, this is 180 degrees for the 2 hydrogens, but that's not true. Instead, you know that it should be closer to 109.5. In fact, the lone pairs will squeeze it down a little bit, so it's more like 104.5. But you would never draw water in a linear fashion. Water is instead bent. So the key thing to recognize is that water is bent, and it's 104.5 degree bond angles in water. This right here offends me because these angles are just simply too acute. Otherwise, I don't really have a problem with it. When you are trying to draw out a staggered conformation thing, you're going to aim for 109.5 degree bond angles on the baseline, and what that will actually look like is more like 120 as a first approximation. So something more like that is better. Now, why do we care about this? Fundamentally because organic chemistry is about understanding the structure and how molecules react, organic molecules, which means that you need to be able to draw them well. But moreover, the reason why they are the way they are is because of fundamental underlying atomic orbital considerations. And because of where the orbitals are, this is much closer to the reality than that is. And if you have this mental image, then you need to adjust that. It looks a lot more like that. You should treat it like that. Likewise, there's reactivity considerations when you have an oxygen that looks like this as opposed to like that. So make sure that you're drawing things well. This is the way you might have been able to draw it in previous classes. This is the way you need to draw it for this class. So learn to draw the organic structures according to the bond angles that they should have. Which means that if you have 4 things that you're trying to spread out in space, you're looking to have 109.5 bond angles. And that's what it looks like when you have something more complex. And then if you're trying to represent 3 things in space, like say acetone, you would want to represent this with 120 degree bond angles as implied by drawing it out that way. Make sure you're using the right bond angles for the situation. And again, the reason why this is the way I'm representing it is because of the underlying atomic orbital issue. So the hybridization of the central carbon here is going to be sp3. We'll talk about this more in a separate video. The hybridization of this central carbon is going to be sp2. It only has 3 bonding areas, so this is going to be an sp2 hybridized carbon. Here we have an sp hybridized carbon, and it will be sp on both sides. sp3 hybridized carbons want to be 109.5. sp2 hybridized carbons want to be 120. sp hybridized carbons, of course, want to be 180. Make sure you're drawing molecules the right way.